wanted to work through an example that involves several different forces. This problem involves the gravitational force, tension force, normal force, friction force, and it also involves this concept of equilibrium, that when the sum of the forces on an object is zero, that object is in equilibrium, meaning it's at rest, it's staying at rest. If it's in motion, it's staying with that motion. And so this problem involves these different forces and involves this concept of equilibrium. We're told we've got an arrangement of two masses, one hanging from a cable or a wire or string attached to the other, and the other is atop a table. And this system of two masses that we see in the sketch is in equilibrium. Neither block is moving. The sum of the forces on both blocks must be zero. And we're going to use that equilibrium condition, that the sum of forces on both blocks is zero, to investigate the forces that are acting on the blocks, and in particular, find the friction force and friction coefficient between the block that's sitting on the table, between that table and that block. So let's see if we can do that. There's almost no calculation in this particular problem. All there is in this particular problem is really sketching, drawing forces. And I'm going to sketch and draw the forces on these two objects. I'm going to start with the 50 Newton block. Over here on the left. And think about the forces on it. And then we'll move on to the 100 Newton block. I'll put it over here on the right. That's sitting on the table, and think about the forces that are acting on it. Okay, so for the 50 Newton block, there's a gravitational force downwards. That's its weight, and that is the 50 newtons. So that's one force acting on the block. And then it's supported by a string, cable. So there's a tension force also on the block. And if it's in equilibrium, it must be equal and opposite to the weight. So it too must be 50 newtons. So these are the two forces acting on the hanging block, weight and tension, and the sum of these two forces, they're equal and opposite. One's up, one's down, they're both 50 newtons. The sum of the forces are zero, and that's why it's in equilibrium. So that's the situation for the hanging block. Now the block on the table. So that's the 100 Newton block. So there are several forces acting on it. There's its weight. That's 100 newtons in this case. There's the normal force acting on it that's counteracting the weight. That's the force that the table exerts to support the weight. So that normal force must be equal and opposite to the weight. For the horizontal tabletop, it's 100 newtons. And then horizontally, there's a tension force because it's attached to the string that the 50 Newton block is hanging from. That tension force, we've already figured it out, is 50 newtons. And then finally, there's a friction force between the tabletop and the block. That friction force is opposing the motion. So it's opposite the direction of the tension force, which is trying to move the block towards the right. The friction force is pulling towards the left. And if the block's again in equilibrium, that frictional force, I'll call it F, subscript F, for friction. That must be 50 newtons also. And so those are the four forces: weight, normal, tension, friction, that are acting on the block on the table. And just like the block was hanging, if you add all these forces up, they counteract each other. They add up to zero. And so this block too is in equilibrium. Okay, so this was our drawing of a picture of the situation. Part A of the question asked, what is the frictional force? Well, from our drawing, we figured it's balancing the tension force, which is balancing the weight of the smaller block. That friction force is 50 newtons. Second part of the question, B, is what is the static friction coefficient? Well, that frictional force is related to the normal force through the static coefficient of friction. And so this proportionality between friction and normal force through the static coefficient of friction allows us to calculate the coefficient of friction, mu, from the normal force and the friction force. All I got to do is divide the friction force by the normal force. That's 50 newtons over 100 newtons. I can do that in my head. That's 0.5. That's the static friction coefficient. So sort of step back and think about that problem. We got this, moderately complicated arrangement of two blocks of different masses, different weights. One's hanging, one's on a tabletop. They're connected by a string or a cable that is run over a pulley. And we've been able to analyze that situation, investigate that situation, and understand that situation from the perspective of the forces that are acting and the equilibrium of those forces. And by drawing the pictures, making the sketches of the forces, we're able to figure out the frictional force, coefficient of friction. So that's a nice example of sort of analyzing forces, what we call free body diagrams of forces for a particular arrangement of objects.